Hello and welcome back. In the last video, we talked about the different phases of material and also what happens when we either add heat to a material or remove heat from a material. So recall that heat gets the symbol Q, and heat is energy that is transferred specifically due to a temperature difference. There's three different ways heat can be transferred, either through conduction, convection, or radiation. What we began discussing in the last video but didn't officially present under its true name is calorimetry. Calorimetry is the study of how a material changes when heat is either added or removed from it. So we began introducing that in the last video. If material is at either its melting point or its boiling point, and heat is either added or removed from the material, then some or all of the material's phase changes. If the material is at its melting point, the melting point is the point where liquid and solid for that material can exist at that same temperature. And this is called fusion. So the transition between liquid and solid is called fusion. Recall from the last video that the heat that is added or removed from a material is equal to the mass of the material times the latent heat. When we're talking about the transition between liquid and solid, then this latent heat is the latent heat of fusion. So it gets the little subscript F. LF is the latent heat of fusion. Again, those values, table 14.2. If the material is at its boiling point, now it's between the phase of liquid and gas, and that is vaporization. So we have the same formula, but notice that L has the subscript V. L sub V is the latent heat of vaporization. Those are different values for different materials, also given in table 14.2. So let's look at an example of this. So we can read from table 14.2 that for water, the melting point is 0 degrees C. And the latent heat of fusion, also read from 14.2, is 334 times 10 to the third joules per kilogram. It's worth mentioning that table 14.2 for the latent heats uses units of kilojoules per kilogram. So be careful there. We want to have standard units, and I've immediately converted it to standard units. So what if we have 1 kilogram of liquid water at 0 degrees C, so it's at the melting point, and we pull out from this 1 kilogram of water at 0 degrees C 167 times 10 to the third joules. Notice that 167 times 10 to the third joules is exactly half of the 334 times 10 to the third joules per kilogram. So we're removing 167 times 10 to the third joules of heat energy. What would we have left? Well, if we pull out exactly half the latent heat of fusion and we multiply that by the mass, what we're going to have left is exactly half of a kilogram of solid water and exactly half of a kilogram of liquid water. Because in order to change the complete phase of the material, I would need to have taken the 1 kilogram times the latent heat of fusion, the 334 times 10 to the third joules per kilogram. I would need to have removed a total of 334 times 10 to the third joules to make a transition of all liquid to all solid. But I've only pulled out half that amount. So what's left? Well, what's left is I've got half in the form of solid water or ice, and I've got half of the mass in the form of the liquid water, all of it at the temperature of 0 degrees C. The temperature does not change until all of the phase has changed. So we only get partial phase change when we only take out some of the heat. If we take out all of the heat necessary to change a mass M's phase from one phase to another, then we get a complete phase change. If the material is not at the melting or boiling point, then if you add or remove heat from the material, you get a change in the temperature for the material. And remember that the equation that governs that we introduced in the last video is Q is equal to mc delta T. So remember, C is that specific heat that is material specific and is listed on table 14.1 from your OpenStax text. So let's say we have 1 kilogram of liquid water at 50 degrees Celsius and we remove 3,000 joules of heat. So the Q that we will use in the equation is going to get a negative sign because we're removing that heat. So Q is going to get plugged in as a value of minus 3,000 joules. So what's the new temperature when we pull out that 3,000 joules of heat energy from the 1 kilogram of liquid water at 50 degrees Celsius? So I take Q is equal to mc delta T and I solve for delta T. When I isolate delta T, I get Q over mc. Plugging in the values, this is minus 3,000 joules of heat energy that we have removed from the material. The mass is 1 kilogram, and the specific heat looked up in table 14.1 from your OpenStax textbook is 4,186 joules per kilogram per degrees C. So notice that the joules will cancel and the kilograms will cancel, and the degrees C that's in the denominator of the denominator will flip up into the numerator. And when we plug these values into the calculator, we'll get minus 0.72 degrees C. So the temperature change of the 1 kilogram of water at 50 degrees C when 3,000 joules of heat energy is pulled out of that water will be reduced by 0.72 degrees C. So we will take these concepts and we will apply them to a problem in the next video from the textbook so you can see how to work systematically through the problems that you will be looking at as well. We'll see you next time.